Hey guys, this is your last section of notes for chapter 11. I have section 11.3, day 4 here. And we're still doing area inside polar curves, except now they just get a little more complicated. So we might have to look at getting rid of some areas that we don't want and just focus on the area that it's talking about, things like that. So same formulas, I don't have to show you, I don't really have to teach you anything new, just kind of show you some concepts and I have good news and bad news. The bad news is in your homework for this, in my math lab, it keeps saying find the exact area in this portion of the curve, which means you're going to have to evaluate these integrals by hand. But the good news is you only have to work out 4 of them. So it's only a 5-question homework assignment, and you only have to work out 4 of them. So it says just find the area for number 7. Just find the area inside the smaller loop of this limacone. So if you graph it on your graphing calculator, you'll see that it starts here and it goes this way. Comes back to here, makes the inner loop, and then makes the bottom half of the big loop. So all we want is this area in here. Okay? The problem is if I start with theta equals 0, look at those R values that it's going to give me. It's going to go from here all the way out to here and then to here. And you can see that that's way, way, way too much area. We don't want all that. So I would totally encourage you to think about, okay, I don't want to start my angles at 0 because that's going to give me way too much. Where do I want them to start? Well, when theta is 0, if you sub in 0, you get 2 times cosine of 0 plus 1. So R is 3 to start out with. So when theta is 0, this length right here is 3. And you can see that the length is going to change and change and change until the length becomes 0. And now the length, R, 0 again. So you see when so R starts out being 3, and then it's 0, and then it's, something, and then it's 0 again, and then it's going to work its way back up to 3. So to find just the area of the inner loop, I want to limit theta to start here when R is 0 and to stop here when R is 0. Let's find those theta values. And you can totally do this by looking at the table function on your graphing calculator. So you've got your table function set up when, I've got this backwards. Theta should be in this column, R should be in this column. It's labeled correctly, but it's kind of like, I'm kind of misleading on my independent and my dependent variables. Anyway, you can see that when theta is 0, R starts out being 3. I would like to find out the first time that R becomes 0, what's that angle measure? And if you're counting if you have delta theta is pi over 12, you can figure out what this angle measure is. That's when we're going to start it. And then when is the next time that R is 0? That's where we're going to stop it. And if you look that up in your graphing calculator, it looks like it starts at 2 pi over 3 and stops at 4 pi over 3. So what we're going to do is we're going to go here, 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 here. Just like that. So I've got 1/2 R squared d theta, and we just figured out where we need to start it and stop it. So if I'm going to find the exact value, I need to work this out by hand. So the first thing that I did was I pulled the 1/2 out, totally got that out of my way, and then I FOILed this. Now when you look at these 3 terms inside here, this is going to be an easy term to do an antiderivative on. This is going to be an easy term to do an antiderivative on. You're not going to be able to do an antiderivative on cosine squared. So, surprise, you need to use a trig identity to break this down into something smaller that you can do an integral or an antiderivative on. So the identity that you're going to use is you're going to replace cosine squared with this. So write that down, keep it handy. If you need it for your test, I'll be sure and warn you. But you're probably going to use it a few times throughout your notes, or throughout your homework, sorry. Okay, and then I simplify, got my fractions here. That's a 2. What did I do? Oh, so a 4 times this term just gets me 2 cosine 2 theta, and a 4 times my 1/2 gets me 2, just the integer 2. And I took that integer 2 and added it to this one and simplified before I start doing my antiderivatives. So you can see that I did my antiderivative of each term. I'm getting ready to sub in those values. Again, I subbed in the values and multiplied when necessary because I kind of tend to lose track of things. And it was way more fun setting up the integral than it was working with the fractions at the very end, but whatever. This is how it turns out. And you can see that this isn't an easy, like if you try to do this on your graphing calculator and think, I'm just going to do it on my graphing calculator and then divide the whole answer by pi. That's not possible because your decimal answer will be irrational because of 2 things. Because pi is irrational and so is radical 3. So there's no way, I don't think you can come up with this out of the decimal answer that you're going to have on your calculator if you choose to try to take the shortcut. Okay, next one. It's telling me, okay, now we've got 2 polar functions. We've got a circle with radius of 1, and we've got this. So here's my circle with radius 1. It would start here and it would go this way. And then here's the other one, let's see, starts here. I think this is a cardioid. It stops there. We want the area of the shaded region. If you started with the blue, think about what's the length of R when it starts. And the length of R is going to be when it starts, when theta is 0, it's going to be right here. And then it's going to go to here, and then to here, and to here, and to here. Now, that's a good start. Let's find all of that area. But you can see that I'm finding the area of stuff that I don't want. This portion right here is white, and I want to exclude this. So I'm going to work on finding the area of the blue. So I think I would do this area, and I could just double it to get this down here, right? So I can just do it for 1 quadrant and double it to get this, and then I'll work on the pink area that we want to exclude. All right, so blue, first of all, I can say, I'm just going to go from 0 to pi over 2, just a quarter of the revolution, from 0 to pi over 2, 1/2 r squared d theta, but then I need to double it to get that bottom portion, right? There are other things you could have done. You could have done, instead of doubling it, just go ahead and go from 0 to pi or whatever. These cancel out. Or you could ditch calculus altogether and say, well, good grief. It's just, let's see, half of a circle with radius of 1. You just use area formula. You didn't even have to use an integral on the blue portion. The pink portion, different story. Okay, so what we want to do after we get all that blue, then we're going to need to subtract the pink. So the pink is going to go here, 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 and stop. I could just do that and double it. So if you watch the pink graph starts here and goes around. So I know I want to start my pink area at 0, but where do I stop it? What angle puts us right here? I think the easiest way to do this is look at your table, and you know that your blue radius is 1. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Therefore, your pink R value that you're looking for is 1. Find that angle that goes with it. And I found the angle to be pi/2. Theta equals 0. Theta equals pi/2. So for the pink, I'm going to start it here and stop it here. That just gets me the top part, and I'm going to double it. 1/2 r squared d theta. And ultimately, I'm going to take the entire blue area that I found, which is too much, and I'm going to subtract the pink area that I found, and that's going to get me the gray shaded region. So, kind of same concept. My 2 and my 1/2 cancel. I foiled. You're going to have to use a trig identity to get rid of this so you can do an antiderivative. There's my trig identity. I kind of simplified in my head before I did an antiderivative, so this is a positive 1. This is a positive 1/2, which gives me 3/2, and when I do an antiderivative on it, I threw a theta on there. Sub them in. Changed colors to black. I'm not sure why I did that. My pink area here is 3 pi/4 minus 2. And again, remember, we need to take blue area minus pink area. Blue area minus pink area. This gets me the shaded region. All right. I love this. I love doing this, these types of problems. But I can tell you that I super struggled with this my first year teaching calculus, BC. For example, in the homework when I tried this, so struggle is real. This was my first number 1. Second try, third try on number 1. And keep in mind, you get 3 tries per problem. So this was really working out the problem 9 times. Finally, I got number 1 right. And my biggest problem was I don't think I really understood what R represented. And once I learned that, it just became super cool. So I'm going to stop talking. You can shut the video off, and I hope you have fun with your homework.